Hi everyone. So today we are covering section 6.6, which is surface areas. So this, in addition to all of the previous sections that we've gone through, has a lot of applications to the physical world. In particular, a very common application would be you have some type of weird shape that you are machining, and you'd like to know how much paint you're going to need for this, which is directly related to the surface area. You can use calculus to figure this out. I also know that in a lot of aerodynamic calculations, you need to find surface areas. And the book also mentions that for biology, when you're looking at cell membranes and you're looking at the inflow and outflow of certain chemicals, you're also doing surface area calculations. So this has a lot of wide-reaching applications in the real world. So what I'm going to go through in this lecture is I'll go through a derivation using integrals of how to find the surface area of things. Specifically, we are going to talk about surface areas of solids of revolutions, so anything rotated around an axis, similar to the previous sections we've talked about. And then I will also go through a few examples as well for how to find these surface areas. All right, so let's start with figuring out a formula for these. So if I take a picture, which I have right here, and we look at the surface area of some solid of revolution, and we want to break it up into these really small pieces so that we can use integrals to add up all the small pieces, we notice that it kind of looks like part of a cone, right? So what ends up happening is that as we get smaller and smaller and smaller pieces, the part of the curve we're looking at looks more and more and more like a straight line. And so the surface area is going to be better and better and better approximated with the surface area of part of a cone. So in order to figure out our formula, we need to have a nice formula for the surface area of a cone, or at least part of the surface area of a cone. So if we think about it, this last panel right here on the right kind of looks like a flipped version of the segment we're talking about in figure 6.63. So in order to figure out what this surface area is going to be, we can just take the surface area of the bigger cone, subtract out the surface area of the smaller cone. So the surface area of the bigger cone, S of B, well, this is just given by the formula pi times our radius times the square root of radius squared plus height squared. So if we plug in actual specific things for this problem, right, we know that our radius is this distance right here, and that's given by f of b, and then our height is given by b. So this is actually equal to pi f of b square root f of b squared plus b squared. S of A, the surface area up to point A, going to be the exact same thing. Now we're just going to have A instead of B. So this is pi times f of A, this is S A, times the square root f of A squared plus A squared. So now, if you were to work out all of the algebra, and I'm going to be a bit hand-wavy here for this part, because this is just a derivation to get us to the formula. If you would like a better in-look at kind of the details behind this, definitely take a look at the textbook. It has a really good explanation of how you can formally get this integral. But I'm going to be a bit hand-wavy so we can just get a basic idea of where this formula comes from. You never really want to use formulas that you don't know where they come from, because then you don't know if you're getting strange results or maybe the formula doesn't quite work for certain problems. So that's going to be why I'm going through this. But if you take this and you subtract s sub b minus s sub a to get this surface area right here and do some algebra, well, this is just going to be pi times f of b plus f of a times the length of the segment right here, where this length is going to be L. And we can write out the formula for L as being, let's see, b minus a square root of c squared plus 1, where our function is given by c times x. Okay, so the nice thing, though, is that in the previous section, right, we talked about how to calculate lengths of curves. So we can actually use our integral approximation, our integral formula. It's not an approximation, it's exact, our integral formula for this L, right? And if you remember back, this is going to be the integral from a to b. These are different a's and b's than above, of 1 plus f prime of x dx. And so the other thing to note, right, we're going to be shrinking these b's and a's closer and closer together. So we're looking at smaller and smaller of these conic sections. And so f of b plus f of a, if we're just kind of looking at one specific point x, is just going to be 2 times f of x. So our surface area formula is the integral from a to b, where these are the x value bounds, of 2 pi f of x. So that comes from the pi and f of b plus f of a. And then we also add in this length, and we get this is 1 plus f prime of x. And this is coming from the length. And then taking the integral with respect to x. And that is the formula that we'll be using for surface areas. Okay, so that's where it comes from. Now let's do some examples for how we can actually figure out these surface areas. So the first example, which is an example from the textbook, is figuring out the surface area of this section, 2 times the square root of x, from 1 to 3. So in this case, our leftmost x value is going to be 1. So our a is 1, b is 3, and f of x equals 2 square roots of x. So if we look at the surface area formula, we have most of the parts. We have the bounds of our integrals. 2 pi is given. We know what our f of x is. The only thing we don't know in the formula is f prime of x. So f prime of x, the derivative of 2 times x to the 1/2 is 1/2 times 2x to the negative 1/2. Negative 1/2 comes from 1/2 minus 1. So this, the 1/2 and 2 cancel to give me x to the negative 1/2. Okay, so plugging everything into my formula, I get that the surface area is equal to the integral from 1 to 3 of 2 pi times 2 square roots of x times 1 plus, excuse me. There is a mistake in this. My length formula should be given by f prime of x squared. Apologies for that. There should be a squared there, squared here, which means that when I take the squared of f prime, I'm going to get x to the negative 1 or 1 over x. 1 over x dx. Okay? I can bring out the 2 pi, and I can also, 4 pi. I have 2 different 2's. 4 pi. And when I'm multiplying two square roots, I can just multiply the inside part. And so I'm going to get x times 1 plus 1 over x, which is the square root of x plus 1 dx. So similar to the length of curved section, we talked about how because there are square roots in this, you'll generally use u substitution, or possibly you'll show that the inside function is a square to get rid of the square root. The same thing applies here. Those are the two techniques we at least know right now for dealing with square roots inside of integrals. In this case, I can use a u substitution of x plus 1, which means if I take derivatives of both sides, I get du equals dx. My x equals 1 bound. If I plug that into my formula right there, will translate to u equals 2. My x equals 3 bound. Well, 3 plus 1 is 4, so that translates to u equals 4. So taking all this information, we still have the 4 pi out front. My bounds now become from 2 to 4, integral of the square root of u du. Okay? 4 pi, integral of u to the 1/2 is going to be 2/3 u to the 3/2. 2/3 u to the 3/2. And this is evaluated from 2 to 4. So if you plug everything in, you subtract out u for when u is 4 from when u is 2, we're going to get that this is equal to 16 pi over 3, 4 minus the square root of 2. So that is going to be what the surface area of this shape is. So if you were trying to paint either the inside or the outside of this shape, this is how much paint you would actually need for this shape. Okay, so now we are going to talk about a relatively famous problem. It's kind of more of a philosophy problem than anything, but it's something called Gabriel's horn. And I have a picture of what Gabriel's horn looks like right here. Gabriel's horn is just going to be the shape that you get when you rotate the curve y equals 1 over x around the x-axis, and you take the integral as it goes to infinity. So the interesting thing about Gabriel's horn is we're going to show it has a finite volume, but it has an infinite surface area. So this is really interesting, right? What this means is that if you had some real-world version of Gabriel's horn, what you could do is you could take a finite amount of paint and pour it into the horn and cover the entire surface area of the horn, which is why it's kind of a paradox, right? It doesn't really feel like this is something you should be able to do. Now, obviously, this doesn't work in the real world, right? Paint has atoms in it. It can only get so small. We can't have infinitely long shapes in the real world. But it's still an interesting thing to think about, that we can have these shapes with finite volume, but infinite surface area. Okay, so this has a slight review because we will calculate the volume of Gabriel's horn. So if you recall the formula for volume, and we're going to take this from 1 to a and see what happens when a gets really big. So volume is going to be integral from 1 to a of pi 1 over x squared dx. Okay. So if I do the integral, I have an x to the negative second in there, and I have a pi. So the x to the negative second, I'll add 1 to get x to the negative first, and then I'll get a negative. So this is negative pi times 1 over x evaluated from a to 1. Okay, so plugging things in, I get that this is pi times negative 1 over a plus 1. So I plugged in a and then I subtracted out when I plugged in 1. Now, as a gets really, really big, we write as a goes to infinity. What ends up happening, if I take 1 over a huge number, that's going to be basically 0. And so my volume is going to be pi. Okay, so it has a finite volume, like I said. But now we're going to show that it does indeed have an infinite surface area. So our surface area calculation is the integral from 1 to a of 2 pi times 1 over x. And we also need the square root of 1 plus f prime of x squared, so we need f prime. Derivative of x to the negative 1 is negative 1 over x squared. Negative 1 over x squared. I just bring down the negative 1 and decrease the exponent by 1. So this is 1 plus negative 1 over x squared, all squared dx. Okay. So the little technique that we're going to use, or kind of trick we're going to use in this case, and this is not something that you necessarily need to know how to be able to do, but it is something that is going to come in handy for this specific problem. This right here, this square root, is going to always be greater than or equal to 1. So if I take an integral and I take out part of it that's greater than or equal to 1, I'm going to get a smaller integral, right? So this surface area is going to be greater than or equal to something we can take the integral of. The integral from 1 to a of 2 pi over x dx. And the reason we do this, right, is we're trying to show that this shape has an infinite surface area as this a value keeps going out and out and out. And so if we can show that it's bigger than or equal to infinity, well, then it has to be infinity. So integral of x to the negative 1 is the natural log of x. This is the exponent rule that doesn't follow the rest of them, where you add 1 and divide or multiply by the reciprocal. So this is equal to 2 pi natural log of x evaluated from 1 to a. And now we can plug in a and 1. Remember that the natural log of 1 is 0. And so we get that this is just equal to 2 pi natural log of a, right? And as a gets really, really big, natural log will get really, really big, albeit a bit more slowly. But as a gets really, really big, the surface area also gets really, really big. And there we have it. So we have this weird shape that exists in infinity and really only in math world, but it has an infinite surface area and a finite volume, which is a really interesting result. Okay. So we're going to do one more example for this lecture, and we're going to be talking about rotating now around the y-axis instead of the x-axis. Similar to the last 4-ish lectures, all we're going to do is we're going to change our integral to be in terms of y instead of in terms of x, and we're going to make sure that our integral bounds are now y values instead of x values. So around y-axis, we're going to get an integral from a to b, where these are now y values of 2 pi f of y square root of 1 plus f prime of y squared dy. Same formula, just y's now instead of x's. So let me pull up a picture of the problem, which we have right here. There we go. Okay. So we are looking at this weird kind of shape of a cone that's sloping downwards, and our bounds are going to be a equals 1, and we're going to go to b equals 2. So a equals 1 is our bottom y value, b equals 2 is our top y value. Now, this function we have is not in terms of y, it's mixed variables, but we can take this and solve for x in terms of y to get our specific function. So in particular, we have 4y cubed minus 10x square root of y plus 5 equals 0. To get x by itself, we want to isolate all of the x terms and then divide. So I can add 10x square root of y to both sides. I get 10x square root of y equals 4y cubed plus 5. And now I divide both sides by 10 square root of y to get x by itself. Divide by 10 square roots of y, divide by 10 square roots of y. So if I simplify this, I get that x is equal to 4/10 or 2/5, y to the 3 minus, right, because we're dividing, so it turns into minus y to the 1/2, or minus 1/2. So it's 3 minus 1/2, which leaves us with 5/2. 5/10 is 1/2 plus 1/2. And then we have y to the negative 1/2 because we're dividing by the square root of y. So for our surface area formula, as we've talked about before, we need the derivatives. So this is our f of y. F prime of y. If I take the derivative of 5/2, I multiply by the 5/2. 2/5 times 5/2 is 1. And I add 1 to the exponent, so I get y. Oh, sorry, I was taking an integral there in my head instead of a derivative. Okay. Right when I take derivatives, it's very easy to mix up derivatives and integrals, especially when you're doing both of them a lot. So just be very careful when you're doing this in your own work to not mix up the two. Okay, derivatives. When we take derivatives, we subtract 1 from the exponent, and we multiply by whatever term is in the exponent. So we still have 2/5 times 5/2 because that's what was in the exponent, which will become 1. And we're now left with y to the 3/2. Okay, same process for the second term. We get that this is 1/2 times a negative 1/2 from the exponent, and then we subtract 1, y to the negative 3/2. Fully writing this out, y to the 3/2 minus 1/4 y to the negative 3/2. And now we can plug everything in. So we get that this surface area, just starting by pulling a 2 pi out, 2 pi integral from 1 to 2 of 2/5 y to the 5/2 plus 1/2 y to the negative 1/2, and then a nasty square root, which I guess I'll write on the next line so it doesn't get cramped. This is multiplication here. 1 plus y to the 3/2 minus 1/4 y to the negative 3/2 squared. Okay, so we are about to enter a phase where there is some pretty nasty algebra coming up in order to simplify this integral. You can skip forward to probably a couple minutes in the future to see the final result. Basically, what we'll be doing is we're going to take what's inside of this square root right here, and we're going to try to rewrite it as a square. Reason we're doing this is that if you think about it and try to pick a u for u substitution, none of them will quite work how we want them to. And so the next step we should probably try to do is make the inside of the square root a square. So let's talk about what the inside of this square root is. We have 1 plus y to the 3 halves minus 1/4 y to the negative 3 halves, and then squared, so the same thing. Let's expand out the squared term and see what we're left with. So if we do this, we still have the 1. If we multiply the first terms out together, 3 halves times plus 3 halves is going to be 3. So we have a y cubed. The outside terms, 3 halves minus 3 halves will be 0. So the y's are going to go away. And we're just left with minus 1/4. So this is y to the 3 halves. And then negative 1/4 y to the negative 3 halves. Same thing happens with the inside. The terms are just flipped. So we have a minus 1/4 again. And finally, if we look at the outside terms, the 1/4 will give a 1/16, and we have a y to the negative 1/3. Okay, so we have a 1, and then we have a minus 1/4 minus 1/4, which is y cubed plus 1/2 now, plus 1/16 y to the negative 1/3. Now, if we look at this right here looks very similar to what's above without the 1, right? The only difference is that instead of a minus 1/2 that we have here when we combine these, we have a plus 1/2. And so what this means is that if we come back to our original term without the 1 right here, and we take both of these and make them positive, well, that makes this and this positive, which leaves us with this positive 1/2. So we get that this is actually equal to y to the 3 halves plus now 1/4 y to the negative 3 halves squared. Okay, so if you don't trust me on this step, definitely check it out, make sure you FOIL it, and see that it works. This is fairly common where the inside of your square root will just be a flipped sign of what it normally is. So it's always a good thing if you are doing these calculations to just double check, see if that works, and if it doesn't, maybe try something else as well. But that tends to be fairly common for these. Okay, so coming back to our original problem, replacing what was inside the square root with this, we have our surface area, still 2 pi, still integral from 1 to 2. We now have a 2/5 y to the 5 halves plus 1/2 y to the negative 1/2. But our square root now becomes a squared, so the 2 will cancel out. We're left with y to the 3 halves plus 1/4 y to the negative 3 halves dy. And this is great, right? So what we can do here is that we can take these two equations, we can multiply them out. We're just going to get a bunch of terms with y to some power in front of them, and then we know how to take the integral of these terms. So if I do this, 2 pi, integral from 1 to 2, the first terms, 3 halves plus 5 halves, will be 8 halves, or 4. So I have 2/5 y to the 4. The outside term will leave me with a 1/10. And I have 5 halves minus 3 halves, or 1. So this is 1/10 y. The inside terms are going to leave me with a 1/2 y as well. And finally, the last term is going to leave me plus 1/8 y to the negative second from this negative 1/2 plus negative 3 halves dy. Taking some integrals, 2 pi, integral of y to the 4th is going to be 1/5 y to the 5th. So this is 2 over 25 y to the fifth. Integral of y is 1/2 y squared. So this is plus 1 over 20 y squared. Same thing with this y term. We could have combined them. I didn't, but this will give me 1/4 y squared. This is multiplied. It's not on the bottom of our fraction right there. Should be a bit more clear with this. Finally, we have this 1/8 y to the negative second. If I add 1 to -2, I'm going to get -1. And then if I divide by -1, I still get a -1. So this transforms into -1/8 y to the -1. Evaluated from 1 to 2. So we can plug in 2, we can plug in 1, and we can get our final solution, which if you do all of that very, very gross algebra, you're going to get 1,377 over 200 pi. And I guess this would be units squared. So that is the surface area of this shape right here. So that is how much paint you would need to cover this shape in a coat of paint.